Hi kids, I wanted to come on here and work a few practice problems with you. Some of you were still having questions about compound events, and I was hopefully going to be able to show you some strategies that might help with those questions. This is the same packet that was mailed home, so if you happen to get a packet mailed to you, then this will help you work out a few of those problems in those sheets. Okay, so first let's take a look at some vocabulary. And the first vocabulary term that I want to show you is called the fundamental counting principle. And that states that when an experiment is conducted that's considered a compound event, or an event has more than one element, the number of possible outcomes can be calculated by considering the number of possible outcomes for each element. Okay? When we were talking about tree diagrams and sample space, we listed out each one of those combinations. So in each event, we listed out the possible outcomes for those. And that's good and great when your possible outcomes are maybe like around 10 or probably no more than 10. But sometimes those outcomes can get to be some pretty high numbers. So you don't want to have to list out like 200 numbers. So the fundamental counting principle can actually help you when you are doing some of those scenarios. Okay, in this, it tells you that the fundamental counting principle can just be calculated as like A times B. If there's 3 elements to it, it'll be A times B times C, and that equals the total outcome. And then it gives you some examples and some step-by-steps right here in this definition. Okay, but we're going to look at a couple of specific problems. Some of them that would be, it just wouldn't be practical for you to list it out as a tree diagram or as a sample space. So the first one we're going to look at is, we're going to look at number 2 right here. Right here. We're going to look at number 2. Okay. So 2A says that spinning a 4-part spinner and flipping a coin. Okay, well, that one would be pretty easy to do as a tree diagram because the first part, it only has 4 possible outcomes and the second only has 2. So if we use the fundamental counting principle, we could easily just do that as 4 times 2 and find that there are 8 possible outcomes. And that one would be fairly easy. But the second part of number 2 says we want to calculate the possible outcomes for pulling a card from a full deck and flipping a coin. So if you know about a deck of cards, there's 52 cards in a deck, and we wouldn't want to list out 52 different elements there for this situation. We don't want to make a tree diagram with 52 parts. So we would use the fundamental counting principle and make it a little easier. So we would list that you have 52 possible outcomes when you pull one card out of a deck of cards, and you have 2 outcomes when you flip a coin. And this would help us out. Instead of listing those out in a tree diagram and then counting them up in the sample space, we can just say that there's 52 possible outcomes for the first one and 2 possible outcomes for the second one, and then we get a total of 104 possible outcomes. And that's a lot easier. That skips a few steps. So this would be the scenario where the fundamental counting principle is a lot more practical to use than a tree diagram and then your sample space. Okay. The next one we want to look at is number 4. And 4A says we're going to spin a 4-part spinner. So if it's a 4-part spinner, there are 4 possible outcomes. And then pulling a card from a full deck, and we know that a deck of cards has 52 cards. Using the fundamental counting principle, we can just easily multiply this, the total outcomes for the first element, the total outcomes for the second element, and 4 times 52, and we will find that there are a possible 208 possible outcomes. Okay, clean that up there a little bit. 208. There. And then the second part of number 4, or 4B here, says we're going to flip a coin, or excuse me, we're going to flip 2 coins. So here we have 2 different elements. The first coin, there is 2 possible outcomes. The second coin, there are 2 possible outcomes. And then we're going to roll 2 dice, numbered 1 through 6. So the first dice has 6 possible outcomes, and the second dice has 6 possible outcomes. So we're going to multiply all of those together, and we're going to find out that there is a total of 144 possible outcomes in this scenario. This one has 4 elements to it, and that would be a very, very large tree diagram and sample space. So there would be 144 possible outcomes for that situation. Okay. Now we're going to go back up to number 1 here. I'm going to change this to red. Okay. And it says, we're going to look at number 1. 3 coins are tossed and 2 6-sided dice are rolled. Okay. So this one has actually 5 elements in it. We're going to do 3 coins. If we were to work this out, there are 2 possible outcomes for the first coin, 2 possible outcomes for the second coin, 2 for the third, and then 2 6-sided dice are rolled. We've got 2 6-sided dice, and we're going to multiply all of these together. And when we multiply this out, we have 2 times 2 is 4, and 4 times 2 is 8, and 8 times 6 is 48, and 48 times 6 will get 288 possible outcomes. Now keep in mind, if we were doing a tree diagram in the sample space, you would be writing out 288 different combinations. So this definitely saves you some time. And I'm going to do some of the ones that have a little bit larger numbers to kind of help you out. Let's see. We'll take a look at number 3. Number 3 says Miranda's jewelry box contains 8 necklaces, 10 pairs of earrings, and 4 bracelets. How many combinations, which contain all kinds of jewelry, can she make? So if she were going to make a combination of all of those, we could list them all out, or we could just use that fundamental counting principle and say there are 8 possible necklace outcomes. There are 10 possible earring outcomes, and then there are 4 possible bracelet outcomes. So if she wants to use all 3 types, we would just multiply this out again, and we would get 8 times 10 is 80, and 80 times 4, we would see that there are 320 possible outcomes or possible combinations of jewelry. And then we'll go down, we'll do the very last one on this page, number 7. It says Jacob must collect a flower, a vegetable, and an herb. In the garden, there are 10 kinds of flowers, 7 kinds of vegetables, and 4 kinds of herbs. How many combinations can Jacob make? Well, if we have 10 possible flowers times 7 possible vegetables and 4 kinds of herbs, we multiply this, 10 times 7 is 70, and 70 times 4 is 280, and I don't see a line, so we'll write that here, 280. So there are 280 possible herb, vegetable, flower combinations Jacob could have. Okay? All right. We'll take a look at this second page here, a couple of these. Now this is going back, we were talking about the sample space and those tree diagrams yesterday. Let's look at number 2. So number 2 tells us that the Kellys are planning a vacation. And we're right here on this number 2. Kellys are planning a vacation. The first day they can go to the zoo or the museum. The second day they can either go to the pier or the dunes. So we'll list that just like this because they could choose any combination of these places to visit, on their vacation. They would have to draw it out like this. And then the third day, they can choose to go sailing, swimming, or horseback riding. If they go sailing, swimming, or horseback riding, and they would have the same down here. There would be 3, 3. Sorry, it's kind of smushed up. But maybe if you list yours out on the paper, it won't be so crowded. Now that would be what our tree diagram would look like if we were to draw that. And this is asking us, it says to draw a tree diagram for each situation. Let's see. Let's try it over here. So to try to keep it from being so smushed up, let's take a look here. So the first day they can go, whoops, I need to change my pencil here. Okay, this isn't quite working right. My pen. Oh no. My new little program's not working right. There it goes. Okay. So they can go to the zoo on the first day or the museum. The second day, they can either go to the pier or the dunes. And since these are all independent, we can list them out separately here. And then the third day, they can go sailing, swimming, or horseback riding. And sailing, I didn't leave myself much room over here either, did I? Okay, I'll draw it up here like this. Sailing, swimming, horseback riding, and sailing, swimming, and horseback riding. There we go. That a little bit better. But this is what our tree diagram would look something kind of like this. Now, if we count this up and we could list this out into a sample space over here, we could list all of these out. The Z, P, and sailing. Let me move me over here. Okay, or Z, P, S, W, or Z, P, and H. And we could list all of these out, or we could just count 1, 2, 3, 4, 5, 6. Let's skip 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I count 12. And we would also have 12 things listed over here in our sample space. But if we go back, we can check it. We can go back and check it. So we would find that there would be 12 possible outcomes. And that would be if we were to use our tree diagram and our sample space. So for the sake of trying to keep this uncluttered, I'm going to get rid of this. Let's just check it using that fundamental counting principle. So there are 2 possible outcomes for the first day. There are 2 possible outcomes for the second day, and 3 possible outcomes for the third day. And we'll find that 2 times 2 is 4, and 4 times 3 is 12. And yes, we have it. So you guys know that I always look for mistakes. And believe it or not, in this answer key, I spent a lot of time working on this particular one because the answer key had the answer as 16. If anybody figure out how they got 16 for the answer, then you need to email me and let me know, because I can't figure out how they got 16, because no matter how I do it, I get 12. Okay? So let's take a look. We'll do one more, and then that'll be all for these practice problems. We'll take a look at this one. And we're going to solve each problem. Now, up here, if you're looking through and reading through some other ways to solve it, another way to represent compound events is using a chart or like a table. And you guys know me, I love tables, but in this particular scenario, I like the fundamental counting principle because I get to skip some of those steps. A table is just, it's pretty much the same thing as doing a tree diagram in the sample space. It's really just kind of repeating that over again. It's just putting it into a table format. And I will say, I will leave it up to you. Whichever one of these strategies works best for you. that would be great. The tree diagram and the sample space is more for the visual type learners. If you can kind of do that math in your head and you can kind of skip some of those steps, the fundamental counting principle may be a little easier for you. If you happen to be just one of those who like to write a lot, maybe you can do the tables. But I prefer the fundamental counting principle. To me, it just seems easier. But for number 2 down here, it says Letitia has red, blue, and black sneakers, blue, tan, and white pants, and black and gray sweatshirts. How many different outfits can she make? Well, that's just asking how many possible outcomes can she come up with the sneakers, the pants, and the shirt. So you can list it all out in your tree diagram if you want, come up with your sample space, or you can use the fundamental counting principle and say that she has 3 possible or outcomes for the shoes. She has 3 options for pants, and she has 2 options for shirts. If we multiply this out, we get 3 times 3 is 9, and 9 times 2 is 18. She has a possibility of 18 different outfits she can make with those combinations of clothes. So I hope these helped, and if you have any questions or if you're looking through any of these problems and need me to work some, just email me and we'll go through them together, or I can always maybe make another video and work through some more problems. So hope y'all have a great night. See you tomorrow.